been a very dry winter. We've had barely any rain. So
Yeah,
actually,
right.
no, I mean, in fact, I know somebody who's living next to the Santa Cruz fire, and they said that they still see stumps, smoking and burning. So until there's really a big drenching, it's not going to be completely out. Then, of course, the mudslides start. So,
Right. Yeah. Yeah. Well, the entire West seems to be kind of
a mess.
dry, extremely dry.
Yeah. 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 And with another dry winter, it's going to be bad next summer.
Let's see what's going on here.
Yeah.
I just blew it.
With the lamp on, I get like reflections on the face.
Carbon dating work, huh?
Thought it best to set the right expectations.
Okay.
All right. So it's 3 o'clock. So 3 o'clock Eastern time, and thanks to all those in Europe who are joining us late in the day. And so the next talk is Ivan Smith talking about quadratic differentials as stability conditions.
Okay, thank you for the invitation. So lots of things have happened in this subject since I thought about it, but most of them have happened in directions orthogonal to ones that I know anything about. So this is a maybe slightly historical talk, but maybe it'll be useful in the grand scheme of the conference.
Right.
So let me start by fixing G at least 2 and a Riemann surface sigma of genus G and a quadratic differential so phi a section of k sigma squared, which I'll assume has distinct zeros. Okay, so then there are 4G minus 4 of them. And I can associate to this the following sort of quasi-projective threefold. So I look at triples of vectors in the canonical bundle K sigma, which satisfy the equation AB plus C squared is phi. Okay, so this is a hypersurface inside the rank 3 vector bundle over sigma, which is K sigma cubed. So it's good to have a sort of picture of this. This maps down to sigma, and the general fiber is an affine conic, and an affine conic in C3 is sort of diffeomorphic and in fact symplectomorphic to the cotangent bundle of S2. And then we have these various zeros of my quadratic differential. And over one of those fibers, we see the singular conic AB plus C squared is 0, which is just sort of a quadric cone. And in this setting, there's an attractive construction due to Donaldson called the matching sphere construction. So here's a little piece of sigma and 2 of the zeros of my differential. And so over those, I have these cone-like singular fibers, and my general fiber is some smooth quadric. And then associated to a path, gamma, between these 2 zeros of phi, I write down something which in each fiber looks like the S2 inside T star S2, and that S2 collapses at the ends. And what I actually write down is a 3-sphere, in the total space of this quasi-projective threefold. So this path gamma between zeros defines a three-sphere L gamma inside Y phi, which is Lagrangian for appropriate Kähler forms. So we can consider the three-dimensional CY3 category, the sort of part of the Fukaya category of Y phi generated by these Lagrangian spheres. Okay, as I vary over all possible paths gamma between pairs of zeros of this differential. Okay, so in fact, there's a natural double cover in this story, which is the double cover branched at the zeros of phi. So there were 4G minus 4 zeros. That means that the genus of this covering surface is 4G minus 3. And H3 of Y phi looks like H1 of this covering surface, but the anti-invariant part for the natural covering involution. And this has rank 6G minus 6. So, well, the Grothendieck group of the Fukaya category of any reasonable symplectic manifold maps to its middle dimensional homology. And we know that part of the data of a stability condition is a linear map on the Grothendieck group of a category to C. So we expect spaces of stability conditions to have dimensions related to ranks of Grothendieck groups. And for various reasons, one's led to conjecture that the space of stability conditions in Thom's sense on this Fukaya category, modulo the group of autoequivalences, is, well, it's the space of quadratic differentials with simple zeros. So maybe I'll call that quad G. So these are quadratic differentials with simple zeros. So this forms an open subset in some vector bundle V over the moduli space of curves, where the fiber of V at some curve S is just H0 of Ks squared.
Can I ask a question, please?
Sure.
So in the top sentence, it says that, so does it, which of the following things does it say? That you are considering the Fukaya category of Wi-Fi, and that is generated by these Lagrangians?
No, that's actually, I'm saying I'm taking the part of the Fukaya category generated by Lagrangian spheres.
Okay, and how far is that from the full Fukaya category?
In this case, we could probably prove that that is the compact Fukaya category. For the cousins of these spaces that I'll come to talk about in a little bit, that wouldn't be true.
Okay, okay, thank you.
This is probably the whole of the compact Fukaya category, but I haven't tried to prove that carefully.
Thank you.
Not at all. Yeah, so since I don't really know my audience, please ask questions whenever. I'm not quite sure what this is aiming at. okay, so this is one thing that we don't know. Let me say a more general thing that we don't know, and then I'll kind of transgress to things that we know a little bit better. So there are also three folds. Fibered over a Riemann surface, where the fiber, instead of being an affine conic, which you could think of as the smoothing of C2 mod Z2, is the smoothing, the Milnor fiber of C2 mod Zm. The sort of AM-1 Milnor fiber. Okay, and we can again write these down as kind of hypersurfaces. So if I now have phi 2 up to phi m in, so phi I is a section of the ith tensor power of the canonical bundle of sigma. And let's suppose that I've fixed some way of writing the canonical bundle of sigma as L1 tensor L2 for line bundles L1 and L2. And then I write down something associated to this tuple of differentials. Which again has the same rough shapes. It's AC equals, and then b to the m plus. And then I form a polynomial out of these various differentials that I chose. Okay, so this is again a hypersurface in a rank 3 vector bundle over sigma. It again maps down to sigma, but now the general fiber is this AM-1 Milnor fiber, which concretely looks like a plumbing of copies of T star S2. So one could again think about, say the compact Fukaya category of this space Wi-Fi. So there's an open subset U inside the sort of vector bundle an open subset in which this Wi-Fi is smooth. Okay, and we could again guess that, so this is viewed as a vector bundle over moduli space of curves. So, and we might guess that U embeds analogously into stability conditions modulo autoequivalences for these more interesting quasi-projective Calabi-Yau threefolds. Okay. But now there's a kind of dimension mismatch, and there's no way this can be onto, for instance, an open set. So this is some sort of high codimension embedding if it exists at all. And so we'll come now to a story in which things are not completely conjectural, the sort of related case dealing with meromorphic quadratic differentials that Tom and I thought about some years ago. But that one would also hope to have analogs in higher rank, the story that we worked out. And I don't really have any idea, in some sense, to me, symplectically, things kind of founder at this point, because the fact that these embeddings, even if we could build them, would be high codimension, more or less wipes out trying to develop any of the symplectic applications that people have used spaces of stability conditions for elsewhere.
Sorry, Ivan. And you've sort of convinced yourself that there are no other ways to deform these manifolds, or there's no way to get a bigger space.
I mean, so Andy once made the very interesting suggestion to me that maybe there was a natural space of affine deformations of these threefolds in which you no longer actually had a copy of, I mean, so I'm not sure if he was quite thinking about this story. I think maybe he was thinking about the case of the resolutions of the vector bundle modulo the cyclic group action, but that contains a zero section. So it contains a compact curve. And you could look for affine versions of those spaces, which were affine bundles, which no longer contained a compact curve. I don't know how to write down something in that setting in which I can exhibit interesting Lagrangian submanifolds and find a Fukaya category. Mm-hmm. That was the most hopeful story I ever heard of, but so. Okay, so the variation that sort of works out somewhat better is to think about meromorphic quadratic differentials. Okay, so we'll now take a pair SD where S is our Riemann surface and D is a non-empty divisor. And sometimes there'll be some further constraints on this, but let's just start with that. And we have a section of KSD squared. Okay, and again, let's suppose for now that phi has distinct zeros and double poles at the points of D. And then one writes down some new threefold. Okay, so this is again a hypersurface but in a sort of slightly twisted bundle. So we've now written the sort of log canonical bundle KSD has a tensor product of two line bundles. And we now consider the equation which says A times C times delta is B squared plus phi, where delta is the section of O of D that cuts out D. So if we imagine that the zeros of our differential don't interact with the points of this divisor D, and you think about being at a point of D, then the left-hand side here vanishes because delta vanishes, and phi is non-zero. So the fiber of this at a point of S lying over D is a new kind of singular quadric, which is just B squared equals constant. In other words, it's given by two copies of C2, because the A and C coordinates vary freely. So now Y phi to S, which still has quasi-projective Calabi-Yau total space, has sort of general fiber T star S2. It has these singular fibers as before at the zeros of phi. And it has fibers that look like the disjoint union of two planes at points P and D. And to be honest, I have to specify what this sort of local topology of the singular fiber is, because I now need a tiny bit more structure, which is that there's a class eta in H2 of Y phi with mod 2 coefficients, which is Poincare dual to the sum of one component of the reducible fiber at P summed over P in D. So there's this class, and it's a standard fact in symplectic topology that if you have a mod 2 homology class on a symplectic manifold, that gives you some way of twisting the signs in the Fukaya category. So the Fukaya category of a symplectic manifold is really a collection of categories, one for each class in H2 with mod 2 coefficients. And so then the theorem that Tom and I proved says that, well, there are some technical conditions in this setup. So if the genus S of 0, then the number of points in D should be at least 5, and always the number of points should be at least 2. And it says that there's a distinguished subcategory let me call it C, inside this twisted version of the Fukaya category in which I twist signs by eta, such that stability conditions on C modulo autoequivalences of C. So I guess there are some sort of decorations here to say it's one component and autoequivalence is preserving that component, is almost our space of quadratic differentials. Okay, so there's a heart here to follow the notation of the paper because we came to love these complications so dearly. So quad heart contains as an open set the quadratic differentials with distinct zeros at points other than D. Okay, that's what I assumed in writing down this threefold. But we have a kind of partial compactification in which a 0 can land on a point of D. And phi then has a simple pole at that point. Okay, and that divisor actually carries an order 2 orbifold structure. Okay, so this is some statement that relates a certain class of quadratic differentials to stability conditions on these sort of categories that are of sort of symplectic geometric origin. So this distinguished subcategory, this is almost surely the subcategory generated by Lagrangian spheres, but for technical reasons, it's slightly difficult to prove that. So.
Could I ask a question here?
Yeah.
So a case that's very popular in physics is genus 1 with a single puncture, which is outside your hypotheses. What is wrong?
We did think about that case. So various things are different with one puncture. I mean, certainly in general, the proof we gave of this theorem didn't work in the case of one puncture. I think it was also true that in the course of proving this theorem, we think about algebraic realization for this subcategory in terms of a certain quiver with potential, and something that naturally comes up is the Jacobi algebra of that quiver with potential and the category of finite dimensional modules over that. That's roughly speaking what the compact category of this threefold with this eta twist is. But you could think about either the Jacobi algebra or the completed Jacobi algebra, and results of Labadini, Fragoso, and Geiss and Schröer and others meant that for more than one puncture in this setting, those two things were the same. But in the case of a single pole, they were not. It really mattered if you completed. And my recollection is that in the case of one puncture, it looked like one would need to use complete Jacobi algebras to get the right answer. But I haven't thought about that point for some time, so I apologize if I've just misled everybody scandalously. So in a few moments, I'll just mention, or maybe I'll just remark, and then I'll say something later on, but one can allow higher order poles. Okay. Then the zeros shouldn't fall into those poles. They should just be honest, sort of fixed poles of some order. And the corresponding threefolds, you just have an empty singular fiber at those points. So you now work over a punctured surface. So maybe I'll call it D greater than 2 to mean the pole order of that point of the divisor is greater than 2. And in particular, that means that you can get your hands on sort of somewhat concrete examples of these spaces of quadratic differentials, where you look at, for instance, space of differentials on P1 with a single high order pole at infinity. And I'll try and write down some of those later. But yes, if the torus with one double pole is a case that you care about, then I think that's a case that we didn't fully analyze.
Physicists definitely care about that case.
Sorry?
Physicists definitely care about that case. It's a very interesting theory.
Right.
I think equally the sphere with 3 punctures. So you only allow from starting from 5 punctures, right?
Sorry, you're so soft-spoken.
So I was saying the sphere, you assume that you have at least 5 punctures.
So on the sphere, we have at least 5 punctures if we're
Yes.
only allowing these double poles.
Right.
But if, for instance, I allow poles of higher order, it's perfectly fine for me to take differentials on P1 with 1 high order pole at infinity and no other poles at all.
Okay.
And some large number of zeros, and those correspond to the sort of type A cases. Those lead to the well-known CY3 categories.
I think we should say that we're not expecting anything radically different to happen in these cases. It's just somehow that our proof didn't go through because we're, for various reasons, and there could easily be a Z2 issue or something like that. But we're not expecting some massive different picture.
No, absolutely. I mean, I would expect that the same statement is, true maybe up to some technicality and maybe with some completion. Although I doubt you'd actually see the completion at this level of the compact category. I would guess maybe something more interesting changes for the wrapped categories of these threefolds, which we never proved anything about anyway. So, yeah. I'm just, yeah. Okay, so what should I say? So now, we again consider a kind of spectral type double cover. So we consider some S hat mapping to S. So branched over the zeros of phi, and if we have them, the odd order poles. Okay. And we think about H1 of S hat naught minus, so this is S hat minus the pre-images of poles of order greater than or equal to 2. And again, we take the anti-invariant part for the covering involution. And this is again by a kind of Lie-Serre type argument looking at this vibration, the third homology of Wi-Fi, and that's actually also the Grothendieck group of this category C. So if we have a stability condition sigma, the central charge should give us a map from this Grothendieck group to C. And we can think about what that is sort of quite concretely. So if this covering map from S hat to S is called Q, so then Q star phi is naturally psi tensor psi for a meromorphic abelian differential. Okay, and we can now integrate that, holomorphic or meromorphic one form over, paths in S hat 0 minus. So Z sigma of gamma is just given by integrating over gamma this psi, where gamma is in what is usually called the hat homology of S, which by definition was this. H1 of S hat 0 minus. And, it's, I think, reasonably standard in the world of abelian differentials that the space of abelian differentials on a Riemann surface has a sort of nice period map, which remembers that differential as a relative homology class in H1 of the surface relative to its zeros. Okay? And this is some cousin of that, but it's maybe more helpful not just to think about the cohomology class of the one form, but to think about integrating this meromorphic abelian differential over paths. Okay, and so then the sort of addendum to the theorem was about the stable objects for these stability conditions. So and the stable objects for the associated stability condition are exactly the saddle connections, or maybe more generally, the saddle trajectories for phi. So I'll draw a picture now, but I'll spend sort of a good chunk of the rest of the talk saying a little bit about the geometry associated to a quadratic differential and trying to sort of say something about what these saddle trajectories look like. Okay. But the saddle trajectories somehow come in two broad flavors. One are what you'll see you should think of as straight arcs between a pair of zeros of phi. Okay. So these are exactly versions of these matching spheres that I was talking about earlier. So here gamma is corresponding to some L gamma, which is an S3 inside Wi-Fi. And then the other kind of picture that one has is something that looks kind of like a family of saddle trajectories that are closed and they move in some non-trivial annulus foliated by parallel circles, which generically ends at a pair of saddle trajectories that run from a zero to itself. Okay, so these would live in a hat homology class gamma whose DT invariant was -2, corresponding to a moduli space of stable objects being P1. Okay? And these would correspond here to a Lagrangian S1 times S2 in Y phi. So remember, the general fiber of this threefold over sigma is T star S2. So over every point over a circle in sigma, you can consider the associated S2, and you'll write down an S1 times S2 in the threefold, which at these endpoints sort of degenerates to an immersed S3 with one self-intersection point. Okay. So let me say a little bit about the geometry of the quadratic differential. So in general, if I have a section of the square of the canonical bundle on some Riemann surface, then locally away from zeros and poles, there's a coordinate in which I can make it look like dz tensor z, dz. Okay. And this coordinate is defined up to translation and replacing z by minus z. So this means that the kind of Euclidean metric in the z coordinate plane is well defined. Okay. And we also get a kind of horizontal foliation that just looks like lines parallel to the real axis with respect to this local coordinate. Okay, so somehow locally on our surface, we have this sort of natural foliation by these lines where the imaginary part of z is constant. And then if phi has a simple zero, this foliation becomes singular and it has a kind of natural trivalent structure. And at, for instance, a double pole, there's actually now a parameter, there's a residue, so phi sort of locally looks like c dz squared over z squared for some complex number c. And if the imaginary part of c is non-zero, then this local foliation is sort of made out of kind of logarithmic spirals that wind into the point. But if, for instance, c is negative real, then one sees just a family of encircling trajectories. Okay? And locally, the metric here is like a sort of half-infinite cylinder. Like a Euclidean half-infinite cylinder. So I had a picture which I sometimes find helpful, not to say that anybody else finds it helpful, but so here I have a sort of sketch of the standard kind of thing that people think about when they're thinking about flat surfaces, singular Euclidean metrics, which is that I have some planar polygon and I can identify the sides by translations. Okay, and what I'll get will be a well-defined Euclidean metric. Okay, But then I could take sort of 3 little extra sides which sum to 0 and kind of force them into this polygon and create 3 kind of half-infinite Euclidean cylinders, which are like neighborhoods of 3 double poles. So I've turned something that had the geometry of a quadratic differential or an abelian differential into the geometry of a meromorphic differential with double poles. And if you imagine bouncing a billiard ball on a table that looks like this, and it sort of bounces according to angle of, incidence equals angle of reflection, well, in a surface like this one up here, you could easily imagine that your billiard ball bounces around forever, okay, and is kind of has wild trajectory, has, for instance, dense or ergodic trajectory if you strike it. But if you imagine this as the surface of your billiard table, this sort of second picture, and you strike a billiard ball, then pretty much inevitably at some point, it will just sort of fall into one of these holes and it will go down to infinity and you'll never see it again. And that's actually true. So it's a sort of, important observation, which we learned from Gaiotto, Moore, and Knightsky, that whereas a classical sort of theory of quadratic differentials the set of theta in S1 such that there exists a straight in the Euclidean metric sort of trajectory for e to the minus I theta phi between 2 zeros. Okay, so this is one of the trajectories of this foliation, but for the rotated differential, or if you prefer a trajectory that ran at a constant angle theta to that foliation, this set is dense in the circle. But for theta meromorphic, with a pole of order at least 2, this set's closed. And there are even special situations in which it could be finite, although that's rather exceptional. So if you expect in the end the saddle connections, these straight trajectories running between zeros of phi to be connected to stable objects of a stability condition, this kind of coarse simplification is likely to make your life a lot easier and is kind of essential to our being able to solve things. Okay, so let me draw a picture of what goes on with this differential. So, if I have this differential, it has some kind of trivalent 0, and suppose phi is really generic. So if it's generic, or if I choose this angle theta by which I rotate it to be generic, I don't expect there to be any distinguished trajectories that run between zeros. There's an open set of angles in which they didn't exist. The zeros of my differential were trivalent for this trajectory. So, an arc there are these 3 special arcs that come out of here, and I would expect them to fall into these sort of double poles that are points of D. Okay, and then maybe there's another 0 which also has things that fall into these sort of double poles. And I get some picture on my surface that starts to look like this. Okay, so this is a sort of generic picture in which these are points of my special divisor D, and these are zeros of phi, and I've drawn the trajectories in this kind of horizontal foliation. Okay. So I cut my surface up into these regions that look like rather standard strips. They actually have, they're conformally equivalent to some strip in the complex plane, the region between two parallel lines. Okay? And I also see these kind of, distinguished at least up to homotopy paths that I could draw between some of the zeros of these differentials, one in each strip. Okay? And these trajectories gamma were meant to give rise to these matching spheres, L gamma in Y phi. Okay? And I have here, a structure that's rather combinatorial and rather rigid. So what I find is that S is cut up into horizontal strips, and I get a finite distinguished collection of Lagrangian three spheres. L gamma, one associated to each strip. And once I have such a finite distinguished collection, I get a kind of distinguished finite dimensional A infinity algebra out of Floer theory. So I can study the Floer cohomologies of these Lagrangian spheres, their sort of total endomorphism group of this object given by the sum of these spheres in this category, the Fukaya category of Y phi, in fact, with this sort of sign twist. So this is some finite dimensional A infinity algebra. And it's a consequence of the fact that I had a meromorphic differential and some of the sort of constraints that come out of that, that this algebra turns out to be the kind of algebra that's governed by a quiver with potential. Okay, so the vertices of the quiver correspond to these Lagrangian spheres. The edges in the quiver record the intersections between the spheres. Okay, and then there's the terms in this potential on the quiver. This is this word in sort of cyclically oriented edges, a cyclic word on the quiver. These record the kind of A infinity operations, or with the holomorphic polygons which contribute to the Floer theory. And in this kind of sketch picture, it's not so hard to see two kinds of holomorphic polygons. So if each of these things is a Lagrangian sphere, well, three of them are intersecting at this one point, and there's a constant holomorphic triangle at that point, and holomorphic triangles define the algebra structure in an algebra like this. On the other hand, associated to each point of my original divisor D, I have a whole cycle of these Lagrangian spheres. They cut out some region in my Riemann surface S, and there's an obvious holomorphic disk sitting here downstairs in S, bound by this finite set of arcs. So I could think about, sections of my bundle Y phi over S lying over that disk. Those would give me holomorphic disks in the total space whose boundaries lay on the Lagrangian three spheres associated to these arcs. Okay? And so those are certain holomorphic polygons that should contribute to this algebra. And saying that things are governed by a quiver with potential essentially says that if you just remember these constant triangles and these rather obvious polygons, then what you end up with really satisfies the A infinity relations. And then there's a certain amount of algebra building on work of others, of Geis, Labadini, Fregoso, and Schröer, that says that you can ignore everything else. Okay, so.
Sorry, question?
Yeah.
Do you have an interpretation of the Hochschild cohomology?
Of this algebra?
Yeah, yeah.
Yeah, so I mean, not proved, but in certain cases where we know these threefolds a little bit better, you can identify the causal dual to this finite dimensional A infinity algebra with, you know, arbitrary modules rather than finite dimensional modules over the Ginzburg algebra, and that with the wrapped Fukaya category of this threefold. And then Hochschild cohomology quite generally is given by this invariant called symplectic cohomology. The trouble in precisely the situation I'm talking about is that this threefold does not have kind of contact type at infinity. It's quasi-projective, but the divisor at infinity is somehow naturally Neff and not ample. And that means that there are certain problems in just defining the wrapped category. So the Hochschild cohomology ought to be the symplectic cohomology of this threefold, but one would have to do a little bit of work to make that a precise statement. And we wouldn't be able to prove it outside of certain special cases, but it's true in, say, the AN case. And there are cases where it's known.
Thank you.
Okay, so as we sort of, you know, we have this space of quadratic differentials. So let's think about the locus where I have distinct zeros and double poles. Okay, and this is some sort of union over, well, there's a combinatorial sort of structure here that will be kind of clear to some and, you know, implicit to others, but there's a structure of an ideal triangulation coming from the fact that these vertices were trivalent. So I get some union over ideal triangulations of chambers where that triangulation is constant. And in such a chamber, I can take the periods with respect to the differential of my preferred arcs gamma. And what that gives me is a map from such a chamber to kind of some power of copies of the upper half plane. And then as I vary my quadratic differential, I can run through the walls that separate these chambers, and the sort of typical thing that happens in a one parameter family is that I go from a picture like this to a picture like this, in which exactly, you know, which poles this particular zero is connected to have changed by this switching to that, because at some intermediate time we had an exceptional event, which that there was actually a straight arc for the differential. So my genericity hypothesis a moment ago was that there were no straight arcs between zeros, but here I have one of these saddle connections corresponding to a stable object of phase 0. So let me sort of, you know, come back to this special example I mentioned earlier, which is where we allow higher order poles. Okay, so if G is, the genus is 0, and we consider differentials, with a single higher order pole at infinity, say pole of order n plus 5, well then the space of quadratic differentials, so, you know, now we don't have any double poles this kind of complication about this kind of heart thing I was mentioning doesn't come up. So this is just the whole thing that we care about. These quadratic differentials are just, you know, appropriate polynomials times dz squared, where these are degree n+1 polynomials with distinct zeros. Okay, and we should want to take these, you know, modulo automorphisms of P1 that fix the point at infinity where our pole is. That would be the sort of natural group that we quotient out by. Okay. So concretely, you know, this looks like product of z minus ai dz squared, where the ai are pairwise distinct, and we can sum them to be 0 by using part of our symmetry group, and that just leaves us an action of the n+3 roots of unity multiplying z by some root of unity. So modulo an action of z mod n+3. Okay. And even more concretely, I think a model that Tom often uses in maybe the simplest case, which is called the A2 case, we end up studying the space of differentials of the form z squared plus az plus b dz squared, okay, where the condition becomes a kind of standard discriminant condition that 4a cubed plus 27b squared is non-zero. Okay, and so now the periods which correspond to the central charges of the associated stability condition are just given by integrating over gamma I the square root of q of z dz, where this was my differential q of z dz squared, and the gamma I are taken from a basis of periods of the elliptic curve, which is sort of the double cover of the plane, sort of given by w squared equals q of z. Okay, so in the end, one's looking at sort of pretty concrete, you know, space of polynomials. The moduli space is some configuration space giving you some distinct roots condition, and you're integrating kind of, you know, square roots of polynomials along arcs between zeros in the plane. Okay, so just let me draw a couple of pictures and end with a question, and then I'll stop. So in this sort of A2 case, this corresponded to triangulations of something with 5 marked points on a disk. The triangulation looks something like that. My differential has 3 zeros, and this kind of trajectory structure I was talking about a moment ago looks something like this. Okay? And you indeed see kind of 2 interesting classes that you could integrate along, being these 2. And so 2 final remarks. So one is an interesting example, or one example that I was always intrigued by was P1 and differentials with poles of orders 2 and 4. Okay? So these differentials have 2 zeros. And if I put the order 4 pole at infinity, then I can naturally draw 2 of these matching spheres. And now the purpose of this sign twist is to make sure that the Floer cohomology of these spheres is actually 0. Okay, but in the untwisted Fukaya category, the Floer cohomology of these two spheres would be C2. And actually in the category that we care about, the only spherical objects in that category look like L gamma and L Tor up to shifts. But in the threefold you would write down in this case, there are kind of infinitely many Lagrangian spheres up to isotopy. Okay? And from the point of view of symplectic topology, the fact that one includes these differentials with simple poles is slightly puzzling. The monodromy around this kind of orbifold locus, I said that to define this eta, I had to pick a cycle representative that lived on one of the two components of my reducible singular fiber, and this monodromy swaps those two components. Okay, and there's no way of kind of filling in this family of threefolds with a threefold at the special points of this divisor without changing the topology of the threefold. There is something you can write down, but it's not something that you'd expect to do ahead of time in symplectic topology. The other remark, and I'll end here, was that I talked about these sort of higher rank threefolds with fibers being more complicated Milnor fibers. So in the next case where Y phi to sigma has A2 Milnor fiber as general fiber. Okay, so this is something that's a plumbing of two copies of T star S2. It retracts to a union of two S2s meeting at a point. Well, I can still form a matching sphere if I use the same S2, like maybe this one, sort of in all these fibers, and it collapses at both ends. But if I just draw a path between zeros of a differential in this setting, there are in principle kind of infinitely many different spheres in the fiber I could take here. This simple four manifold contains infinitely many Lagrangian spheres. So there's another picture that naturally arises of so-called tripod matching spheres, in which you have three zeros of your differential and you have a Lagrangian sphere, L tripod, which lives over a series of arcs where if these spheres were the A and B spheres, you see in the fiber kind of the A sphere, the B sphere, and the Dane twist of one about the other lying over these three arcs. And these pieces glue together to form a Lagrangian sphere. And you can put two of these together meeting at all three endpoints. That gives you a pair of Lagrangian three spheres that meet with sort of Floer cohomology of rank 3 in 1 degree. And so you quickly see that sort of the Donaldson-Thomas theory of the 3-arrow rather than 1 or 2-arrow Kronecker quiver kind of appears here. So now there exist kind of classes gamma in K0 such that the Donaldson-Thomas invariants of n gamma kind of grow exponentially with this n, which is something that doesn't happen in the simpler threefolds that we were thinking about. And I don't know how to see geometrically in terms of drawing pictures in the base and understanding Lagrangian submanifolds whose Floer theory I can make sense of, where the sort of complexity in these answers for the DT theory comes from. So in pictures in which DT invariants count special Lagrangians, there's very quickly things here that we don't understand. Okay, I'm sorry I've overrun for a couple of minutes. Thank you for your attention.
All right, let's thank Ivan. Do we have some questions for Ivan? Or answers?
Is it possible that these threefolds actually have Calabi-Yau metrics? Is that something that's...
It's very much possible, but I think has not been studied. So the I don't believe that the structure of the divisor you see at infinity, and if you compactify them by some reasonable normal crossing divisor, the thing that you get has this kind of Neff divisor at infinity that's not especially attractive. I don't think any of the existing theorems sort of off the shelf apply. But certainly in this meromorphic case. In the holomorphic case, I don't know of work, but maybe there it is known. Yeah, we would want that to be true. Certainly you can write down somehow, you know, 3 form which makes the straight trajectories for the quadratic differential, sort of the Lagrangians associated to those become special in the weak sense that this holomorphic 3 form has constant phase, but you know, they're not special in a more sort of grown-up sense.
What do you mean by that?
Well, I mean that there's no Ricci flat metric in sight
Right,
when one does that. So
Well,
they're
not,
somehow special for the wrong. Yeah.
What's the point? They're not minimal surfaces or something like that.
That's right. That's right.
I think this is related to, well, the question I was going to ask, but also related to the discussion during Tom's talk that we were having. So this is, you know, in physics terminology, this is related to what Greg was saying about field theories with and without gravity. So morally, without gravity means you've got a non-compact Calabi-Yau, and with gravity means it's compact. And actually, to define a completely decoupled, to define a field theory which is completely decoupled from gravity, likely requires the existence of a complete Calabi-Yau metric on the non-compact space. So it could be that what you're seeing, for example, this exponential growth that you were mentioning just now, is related to the fact that these things, those configurations only exist when embedded in a compact setting, and was related to Greg's comment. I don't know if Greg's still around.
I'm here, but well, I don't understand everything Ivan said. My reading of the last comment was a little bit different. I think what he's doing is he's geometrically engineering an SU3 theory. And these are the so-called spectral networks or finite WKB curves that correspond to hypermultiplets in SU3 theory. And in fact, there is a physics paper where these trajectories were analyzed in detail and the exponential growth was actually derived. So Ivan, you were asking for a geometrical picture. I don't know if it'll satisfy you, but there is some discussion in the physics literature about if
right. I mean, I certainly know that one sees this exponential growth from the spectral network point of view.
Okay.
I guess the spectral networks quickly become sufficiently complicated that I don't know how to understand those in terms of Lagrangians, or certainly not Lagrangians whose Floer theory.
Oh, well, okay, sure. So,
you know, a reasonable thing I would think is that if I make these 2 original Lagrangians intersect at 3 points, right, then a natural thing for a symplectic person to look at is the Lagrange surgery, which is now a connect sum of S1 times S2s, and it has free fundamental group. And in the Fukaya category, you would see all the representation theory of that free group naturally show up in understanding your Lagrangian brains.
That's interesting. Okay.
And so if I was looking for interesting objects of class n gamma, I would look at rank n vector bundles over that Lagrange surgery. What I don't know is whether or not there's some way to look at irreducible representations of the free group of larger and larger ranks and to recover the interesting generating functions for DT invariance that seem natural from your point of view. I mean, I've looked at those sequences in the online sequence databases. and I don't know how to get them out of the free group, but maybe one needs to do something, cleverer than that, but still something that doesn't involve finding vast exponentially increasing numbers of actually different Lagrangians. Something like that is the sort of thing that would maybe fit with things that I know how to build and study symplectically, but it might be completely the wrong idea.
Okay, well, let me make sure I did understand you roughly, at least. At the end, you have a bundle of resolutions of A2 singularities over a Riemann surface, and you're talking about the Floer theory of that.
It's actually a bundle of A2 smoothings rather than A2 resolutions. So in my general fiber, the two S2s are Lagrangian, not rational curves.
Okay.
So there's a sort of potentially mirror picture in which I could take, a rank 2 bundle over sigma, divide it by a Z mod M acting fiber.
Okay, I think I was
then try to resolve that cone of singularities.
I see. Yes, that's the case I was thinking of. Okay.
So I'm taking that singular threefold and smoothing it, and the space of, differentials or tuples of differentials naturally sits inside the, that maps to the kind of Kadara-Spencer space for that, singular variety given by taking the vector bundle modulo the fiber-wise group. So I'm looking at the smoothing.
Okay, thanks for that. That's an important clarification. Thank you.
Did you say that would be a mirror picture?
Well, it's not so clear. I mean, these spaces are not quite log Calabi-Yaus because somehow the 3 form doesn't have simple poles at infinity. And that means that the usual pictures that people develop for understanding mirror symmetry for open Calabi-Yaus in terms of Lagrangian torus vibrations don't seem to quite work. But Balázs Szendroy a long time ago, and before him maybe Ron Donaghy and others, studied these kind of resolutions of these bundles, these singular threefolds that had a whole cone of AK singularities, a curve width of AK singularities versus the smoothings. And they suggested in sort of, mirror symmetry of the circa mid-1990s that they appeared to be mirror in the naive sense that they were related by resolution and smoothing.
So that was my other question. Are your manifolds the same as Szendroy's, the ones Szendroy studied? Or?
Well, so Szendroy again was working on this resolution side.
I see. Not on
so apart from so the spaces I'm thinking about were thought about by Donaghy, Dijkgraaf, and Pantev in the case of holomorphic differentials.
I see.
And then these are just tweaked in the case of meromorphic differentials to have the behavior we needed. I should say that a very much studied, I didn't present these threefolds in this way, but in the physics literature, I think people very often study, for instance, a situation where you have a curve in, say, C star squared, and then you think about, or maybe a curve in C squared, and you think about some conic bundle over this given by UV equals F, where F defines C. And and here UV are in C. So yeah, maybe this was meant to be in C star squared. So you have a one-dimensional conic fibration whose singular locus is an entire curve, and that curve is typically taken to live in some holomorphic symplectic surface. And you could view the threefolds I'm looking at as cousins of these. They map down to the holomorphic symplectic surface, which is the cotangent bundle of sigma, and they're C star bundles over the cotangent bundle of sigma, with a discriminant locus being the spectral curve of the original differential. And in the holomorphic case, in the case of a holomorphic differential, that's really true. And in the case of a meromorphic differential, that description needs to be corrected by some kind of blow-ups and blow-downs at infinity. But I think the closest way to connect to threefolds as studied in the physics literature is this one-dimensional conic bundle over a complex symplectic surface.
Are any other questions for Ivan?
I've got a quick question. If we want to try to extend this result to higher rank cases, as you're sort of tempting us to, is there a simple example we should try to think of, like in rank 3? Or maybe Greg can suggest. I don't know, what's the simplest example we could try and consider?
Yeah, that's a good question, but I don't have an answer to it. I guess I saw
literature on rank for on SU3 theories.
Mm-hmm.
There is where these kinds of triangles that Ivan drew appear and are important in the wall crossing story and the spectral network story. And there are even explicit claims for, you know, the spectrum of Donaldson-Thomas invariance. Pretty explicit stuff. And certainly the spectral networks have been worked out in some detail. So yeah, for SU3, yes, there are some physics results.
Mm-hmm.
It's pretty interesting because there are some qualitatively new phenomena associated.
Was the question about SU3 or SU4?
Well,
SU3, my question was.
SU3, I mean, SU3 is the first case, and that's the case where there really are some results on the DT invariance, or the alleged DT invariance. Together with relations to quivers, I should add.
Yeah, the fact that we could describe the Fukaya category in this SU2 case also comes down to some kind of algebraic accident or convenience, which is that what you can always do is you can find certain holomorphic polygons and then you hope to kind of gauge away the rest by formal algebra. And the moduli space of A infinity structures on this algebra in the SU2 case kind of is rigid. I mean, once you've got the right polygons to start with, everything else can be gauged away. And that's already false at SU3. So, you know, one can see this quiver and one can see the right terms in the potential, but one doesn't know that the other terms that will exist coming from holomorphic polygons can be gauged away. So that's already just on the symplectic side, kind of, you know, some difficulty potentially.
Are there any other examples of 3 Biot categories in which one can describe the whole of stab D?
Tom should answer that.
I mean, as far as I know, the answer is no, unfortunately.
But one can describe it if you drop the 3 Biot condition.
Yes, and if you drop the condition that you want, yes, yeah. But no, that's why I would like to extend this result, of course, to get more examples. And in particular, these examples that Ivan's just drawing up there, which look like things like mirrors of local P2. So this thing which is mapping to C star squared and
right. Yeah.
Yes, so the mirror of local P2 would be an example like that. And you know, that would be a great thing to be able to understand stability space for. Yeah, I guess, and physicists understand the BPS invariance of this thing in terms of something called exponential spectral networks. But you know, there's so much, we just don't understand this in mathematical terms yet. I mean, either those or the SU3 examples, we don't really understand.
I mean, the SU3 examples may be easier in that at least we can find kind of the quiver with potential that is right for certain, you know, easy chambers in the locus in stab that's quad we can see geometrically, whereas I think in these exponential cases we don't know anything. On the other hand, in the exponential case we have a guess for what the answer for the space of whole stability conditions is on local P2, whereas for these SU3 theories we really have, I think, no conjectural guess for what all of stab is, and it seems very hard to prove it until they tell us what to prove.
I don't think that's their job, actually.
No, I realize that's why I did giggle to indicate that it was tongue in cheek.
I mean, basically the point is, let's just say this, the point is that, you know, the quadratic differentials case, the dual to the space of quadratic differentials is the tangent bundle to mg. So, you know, so if someone gives you the space of quadratic differentials on a fixed Riemann surface, to sort of double the dimension, all you do is vary the Riemann surface, because the tangent space to that is dual to the quadratic differentials. But now if we're higher ranked, so we've got quadratic differentials and cubic differentials, say, we just don't know how to interpret the dual to the cubic differentials. I mean, I guess it's, you know, h1 of t squared and the tangent bundle squared, and we just don't know what to do with that, I guess. Because somehow the whole space of stability conditions we would expect to be double the dimension of, well, we know it is.
Right.
Just so to go back to right at the beginning of your talk, so the stability conditions are sort of identified with the quadratic differentials on the
right.
But then the stability conditions don't depend upon the complex structure. Have I got it right?
That's right. So the stability conditions on the category is the bundle of quadratic differentials over the moduli space of Riemann surfaces.
Oh, it's the Riemann surface and the quadratic differential.
Yeah, so we're varying sigma and phi.
Right.
Absolutely, that's very important. And in fact, you know, one of the first things that suggested to Paul Seidel and Maxim Kontsevich, who independently suggested that these spaces of quadratic differentials should be spaces of stability conditions, was that spaces of stability conditions always have this natural sort of non-holomorphic GL2 action, or maybe universal cover of GL2, but something that just acts on the C, which is the image of this central charge by real linear transformations. And if you think about the pair sigma phi as a pair of one forms, you can just act by GL2 on the pair, the real and imaginary parts, and you'll get a new pair of one forms, which will be, you know, they'll determine for you a Riemann surface structure with a quadratic differential again. But that action doesn't at all preserve kind of the foliation by fixing sigma and only varying phi. So.
Oh, should we thank Ivan again? So there is some time for further discussions. I don't know who would be appropriate to moderate those.